believe that the recording is as good as a live lecture.
As in the what?
As a live lecture.
Oh yeah.
Wait, you can't ask questions.
Right. So. Okay. Questions?
Oh, was there an error in the homework that was due today? We felt like it was an error. We couldn't show it with your map.
What?
Do you want to go over the previous homework?
Did you get yours?
It was pretty. I made several, like 4 or 5 times.
The map was-
mistakes with the algebra, but it came out though.
Because ours came out except the signs were different.
Oh.
Yeah.
Oh, okay. All right.
And then when I was watching the lecture and I was going back to things he was saying, it all pointed to like
When
an
you put
error.
a square, the square root of -5, did you keep it as -5?
Yeah.
Yeah.
Okay, cool. I don't know that.
Okay.
And there's a whole bunch of errors in the previous one. It doesn't come out to 4, it comes out to 6. So then if you show that,
Okay. So, okay, not sure. We take a map here. To the C. And M plus N times square root of A maps to M squared plus AN squared.
how did you go from there? You're just squaring each term, right?
Only the coefficients.
So
This
what-
one here, yeah, well, if you like, square,
So what happened to your negative? Shouldn't it be a minus sign instead of a plus sign?
you know.
I think you just define it as that. What is it?
You can, but then it won't. Well, let's keep going. Let's keep going. Put it that way.
N of M plus N square root of -8 times M prime plus N prime square root of -8, right? You wanted to work this out.
Yeah.
So, if you multiply this out, on the inside we get M N prime minus A N N prime. Plus M plus N prime. M times N prime plus N prime square root of -2. I just multiply those numbers. I take the product of these, the product of these times -8, and then this and this,
Sure.
which is going to be the square of this. So this is M prime minus A N prime squared. Plus A times M prime plus N prime squared. I took the square of this, I take the square of this and multiply it with
Shouldn't that be a minus A?
A. Here's my definition.
Yeah, yeah, yeah. Oh.
So there's a plus. Yeah, I'm just following the formulas that I wrote down.
Yeah.
Which is, well, let's leave it like this, okay? Maybe we'll work it out a little bit. M prime minus 2A M prime
You forgot your squares over there, yeah.
N squared M prime squared plus A M squared M prime squared plus A N squared M prime squared plus 2A M prime N prime, right? Oh, my arithmetic is right. Now, if I take n of m plus n square root negative 8 times n m prime plus n prime square root of negative 8, I get m squared plus a n
Square
squared
times
times m
Prime
squared plus
A
a
and prime square.
prime
The
squared.
pluses should be there, yeah. What about the minus? Oh, that term cancels.
So
You should cancel them,
this
yeah.
here cancels with this, right?
Yep.
And
All,
the remaining stuff is the same. So if you multiply this one out, you get m squared, m prime squared, plus a squared, n squared, n prime squared, so the product of these. And then you do the cross things. So you have plus a, and you have m squared m prime squared plus n squared m prime squared, right? So this guy here is the same as this.
second term, the same as the second term.
This is the same as this.
Yep.
And the other ones also work, right?
Yep.
Okay, so, I mean, for those people with insight, if you take C, the complex numbers, you want to take N, and then an element goes, so to the real numbers, the map would be that some Z in here goes to Z bar.
Oh, conjugate?
Yes.
There you go.
So, this one here is equal to m plus n square root of negative 5 times m minus n square root of negative 5, right?
Yeah. That's the conjugate.
But, I mean, otherwise I wouldn't have remembered that formula.
So that part works out, but then your other part when you showed, I think that 4 was prime. Is 4 prime here?
So,
Can you build 4?
if you take a equal to 5, right?
Yeah.
No, 4 wouldn't be a prime. 4 is 2 times 2, right?
Yeah.
So, study the image of n. you have zero maps to zero, right? One maps to one, two maps to four, three maps to nine, right? Four maps to 16.
Or you're just squaring each term?
Right, I mean, that's the first part. If you take 0 plus square root of negative 5, this goes to 5, right?
Yep.
1 plus square root of negative 5
It's 5.
goes to 6, right? 2 plus square root of negative 5 goes to 9.
Yeah.
3 plus square root of negative 5 goes to 14. 4 plus square root of negative 5 goes to 19, right?
For 2, isn't it n squared? That would give you 4 times 5.
4 plus 5, right? 2 squared is
Oh, yeah. 4.
this
plus
is
5.
5 times 1 squared.
Yeah. N is 1.
If you took 0 plus 2 times square root of negative 5, this goes to
5 times 4?
20, right?
Yeah. So you're going to do 1 plus 2 root negative 5.
1 plus
29.
and so on, right?
Yeah.
So what did we want?
Sorry. Would
We
you,
were looking at certain prime factorizations, right?
yeah, we want to show 2, 1 plus square root of negative 5, and 1 plus square root of negative 5.
You want to show 2 is prime, yeah.
Yeah, 2 is prime.
2 is prime, right? Yeah.
Can't get
Because,
to.
I mean, if 2 was alpha beta, then n of 2, which is 4, has to be n of alpha, n of beta. But if you wanted to get 4 here, this is the only way to get 4, right?
2.
So if one of the factors was not 1, okay, so anything that is not 1 give you something bigger, right? So here, if you had this, you would have 2, 1. But n of a, which is that unless a is 1, this will be at least 4. Until beta is 1, this is at least 4. So if alpha and beta are not 1, you get at least 16, right?
Accidentally hit the record button.
So 2 is prime. And we had some number that we wrote as the other 6 or so.
I think it was 4. No, it should be 6, right? If you multiply the two radical ones, right, Mark?
Yeah, I think both of them are 6, right?
6 was what?
1 plus root negative.
Oh, I so clear.
I don't know. Is it 1 plus root negative 5?
1 plus root negative 5, and then the other one was negative 1 plus root negative 5.
Which is 6. Root negative 5. That's negative 6, huh?
Huh?
There you go.
This gives me so this is negative 1, this is negative 5, right? This square. So this will give me a negative 6 with a minus negative 6, right? If you like, write it as negative 1, negative square root of 5 times negative 1 plus square root.
Yeah, that comes out to 6.
So you get the square of this gives you 1. The square of this gives you
5.
5.
Yeah. See, so I think there's a discrepancy in what we proved was prime for those two pieces.
Okay, so n of 1 plus square root of negative 5, you calculated was 6. But n equal to 6, I mean, there is no way to write 6 as a product of two numbers below this line, right? If you wrote it as a product like this, you would have to multiply the norms. And you get 1, 6 here, but we have 2 factors, and each of them is at least 4. Yes, at some point I had omitted kind of a radical and written the square or so. So there was some funny thing in what I had written, but principally I was right. And I think the homework, as I stated, it was right.
I guess we're gonna have to redo our homework.
Sure, you have a whole weekend plan.
It's the sign change.
Yeah.
Right now.
Yeah, for real.
But if you want to understand what's going on, you just look at the complex numbers and you say you're taking z times z bar. That's where all the formulas come from. And in the complex numbers, you are used to the product of the conjugate, product and conjugate commute, right?
Yeah.
So, if you did the calculation in using the language of complex numbers, you wouldn't have any trouble.
I don't know, we saw it and we were squaring terms and we got these negatives in there and it just wasn't working.
Okay.
But now that we realize that it's not a matter of squaring it, it's a matter of sticking to your definition in there.
Yeah. Like this entire course, you're supposed to learn that definitions are important. For my 244 before, I tried to find the definition of flux.
Ugh.
It's kind of a funny term, and people don't all mean the same thing, and they use many different names for the same thing.
I just know flux from physics, but yeah, I remember doing it in Calc 4.
Yeah.
The magnetic flux, yeah, and the electric flux.
So sometimes even mathematicians are not good at writing down a clean definition and working with it.
What is the physical interpretation of flux? I don't remember anymore. How much of
The
the
units of flux are per square, unit, square, and time.
Oh, so how much is moving through at a given time, right? What's the area? Yeah, that's what flux was. Yeah, magnetic flux. How many of those magnetic field lines you have going through
But
at a certain
then when
time?
they interpret it, they take the boundary of something and
The shape.
right, and they take what moves across
The shape.
line.
Yeah.
So then flux is not anymore something that has to do with area, because you use the line to define it.
Oh, okay.
And then somewhere they throw the word density at it, and then some people take density serious and others don't. I mean, for some people, flux is the same as flux density. For some people. And then I remember that Newton used the word fluxions, right?
Fluxions? Some kind of particle he's defining, or
For 50 years, nobody was willing to read what Newton had written because he also refused to write it cleanly.
Oh, really? Is this in Principia? Is Principia de Mathematica or whatever?
He should have tried to write it neat and clean so other people could understand.
Yeah. He didn't want to write for the peasants.
No. But actually, he is from a peasant background, right?
No, I thought he was a wealthy guy.
No.
And in the end, he became like a,
He became,
yeah.
but he came from a little house in the countryside.
Oh, looked like a pretty big house when I saw it.
Yeah, I'm pretty sure, you
I
know,
saw it on TV.
he was well-to-do, well-off.
Pretty big house.
The father was a clergyman or something. I know he was like really religious.
But clergymen are rich in England, but no, I don't think he was clergyman. He was in some type of trade, but nothing big.
I don't know. I just know he was really religious in the end, and there was some like, he passed judgment on people.
He passed judgment.
Yeah, yeah.
No, they made him the head of the mint.
Of the mint for coins and stuff like that. Oh.
But in those days, I guess, being head of the mint meant you had to make sure that there wasn't too much forgery.
Oh.
Fun.
So pretty early on, I mean, he may have been in his 30s or so, they made him head of the mint, and then he was in politics and out of science.
Sounds like a really lame title. I'm head of the mint.
Yeah, sounds lame. Okay, so what did I want to do today?
I'll just sit down and talk about life.
I mean, there's one thing that had struck me when I read it, and I had to read it because I was working on a different type of degree and to take a little philosophy. For philosophy, I did model theory and logic. So it turns out, I mean, that your natural numbers are not that innocent.
Innocent?
Like Mark.
Promiscuous.
So what I mean by that is it's very hard to write down axioms for the natural numbers to describe what the natural numbers
Yeah.
are. And if you take your ordinary first order predicate logic and you try to do that, then there are different models for the integers.
For the
They're
integers?
radically not the for the natural numbers.
Okay.
They're not the same. So you can have elements that are bigger than everything else. So there are strange things in there. The axioms don't exclude them. It's consistent. Called non-Archimedean models of the natural numbers. So, in comparison, there is only one, you can exactly write down what the real numbers are. Okay, so, as for people who might end up in mathematics, so what are the real numbers? Axiomatically, what gives you a description of the real numbers? So the real numbers are a set.
They have multiplicative inverses.
You have two operations, right? Addition and multiplication.
Yeah, because subtraction is addition of the
Right.
negative.
You have the laws of algebra, right?
Whatever those
If
are.
you want, go ahead and write down what we're doing.
On the board?
Yeah.
Okay.
So real numbers.
The axioms of the numbers, right?
Axioms of the real numbers.
Real numbers.
Oh, real numbers, my bad.
Okay, so so we have a set S with two operations, right?
Yeah, we have
We have a set
R.
set R.
Mhm.
Okay.
Okay, so don't do the second vertical line there yet.
Just a set, not a set of real numbers.
Set R with two binary operations. And the word binary is not really intimidating, it just means
Two.
you have two elements going through.
Yeah.
Binary operation.
That would be addition and multiplication.
That are associative, commutative, distributive.
That's to write down the actual rules?
No, just, no, just write associative.
Commutative.
Commutative.
Distributive, and what's the last one?
Distributive. We have inverses, right?
Yep.
Multiplicative inverse?
We have neutral elements and inverses.
Neutral element is 0. Inverse
Yeah,
is,
we want.
yeah, 1 over. Oh, is it 1?
Yeah, just like half. Neutral elements and inverses.
Is neutral NE? Well, whatever. Just leave your spelling. Doesn't matter. Doesn't matter. We know what you're saying.
Alright.
In the second draft, you can correct it.
Sure.
So check. I think it's EU.
Sure.
It's all right. Move on, Mark. Don't worry about it.
Neutral.
Okay. So, but then we had more, right?
Yeah.
they are linearly ordered.
R is linearly ordered?
Yes. And we had some axioms that go with it, right? So if x is bigger than y, then x plus z is bigger than y, plus z, right?
Yep.
Sorry, one more time?
In parentheses, you can write x bigger than y. No, just omit the if. Implies x plus z is bigger than x plus z bigger than y plus z. Right? If you add something, then the inequality is preserved, right?
Yep.
Then we had if z is bigger than 0,
If z is bigger than 0,
then x times y, and
Oh.
x is bigger than y, right?
And x is bigger than what?
yep, x is bigger than y,
And
then xz is bigger than, x is greater than y, xz is greater than yz, right? Oh shit. That's just the two, right? That's it, I think, for the linear one.
It may be all. I'm and probably you need if x and y are greater or equal to 0, then x times 1 is greater or equal to 0.
sorry, what was that?
The product of two positive numbers is positive.
Comma y, x comma y greater than 0.
Then x times y is greater than 0.
Right.
Okay.
Yeah.
So, I mean, the question is this what we wrote down minimal or what are we somewhere redundant?
Oh,
So, I don't worry about it.
okay.
So, but which other property does the real numbers have?
Multiplicative inverses.
That we have.
Inverses. Yeah.
Algebra is taken care of. Order is taken care of.
What else is after that? Oh. Bum, bum, bum.
Where do all the calculus books fizzle out?
Continue? No.
Fizzled out.
Fizzle out. Where don't they dare telling you the truth?
With the limit stuff, the epsilon delta stuff. No, I don't think they fizzle out there though. I think they.
They do.
Oh, is that the part then?
There are like 4 big theorems where they say, well, we can't really explain them to you.
Continuity or something like that?
No, one is the intermediate value theory.
Oh, yeah, they just tell you it's IVT and that's it.
One is that continuous functions can be integrated. One is that continuous functions on compact intervals closed and bounded. Assume their minimum and maximum.
Okay.
Why would that be true?
That on an interval they have minimum and maximum. And you know you're gonna have like, you know, the line's gotta go somewhere, so. You know what I mean? Like it's gonna have a minimum or a maximum, right?
But why does the minimum or maximum really have to be there? I
For-
mean, in the rationals, that's not true.
It's because of continuity?
Well, you can define continuity for rational numbers, that's fine.
Okay.
It's because of the linearly ordered?
But for the rational numbers, you don't have an intermediate value theorem.
Because it's not continuous. Even if you define, well,
It's continuous.
Okay.
Well, what do you mean by continuous? What is continuous?
it's smooth and they attach like that. You have that nice attachment.
What is attachment?
That's the real number quality. Those, they, you know, there's this nice
I
ordering
mean,
and
this is actually where Euclid is not rigorous. Euclid didn't really understand.
you use the lambda epsilon, I mean the epsilon delta stuff, right, to explain that though.
Or something?
Or no?
There was no epsilon and delta in the time of Euclid.
Well,
Are you talking about continuity?
that's what I feel like. That's what he's asking.
The limit exists, the.
Yep, from both sides.
Line there, and then the limit equals the.
No,
Function
you can
value.
do limits in the rational numbers.
Okay.
No, there's something called the real numbers are complete, right?
Ugh.
Every bounded set has a least upper bound. Every non-empty set of real numbers has a least upper bound. They don't tell you in calculus.
I remember us having this conversation before.
Okay, so write it down.
Okay, the intermediate value.
Completeness.
Oh, sorry, what was that?
Completeness.
R has completeness?
No, I mean is completeness colon and underline.
Just write the word completeness. And colon and underline. There you go.
Every non-empty bounded set has a least upper bound. Okay, you can erase the right hand side.
Can't recall the definition.
Of a least upper bound?
Upper bound, yeah. I can't imagine the picture.
Well, it's an upper bound and it's the smallest bound, right?
Smallest possible upper bound.
There is no smaller bound. Okay, so it's really the English expression. It's a bound, it's an upper bound, so everything is below, right?
So what you're saying is, like if I define an interval, and you know from 0 to 2, 2 would be my upper bound,
Yeah. To
and the smallest possible upper bound. Yeah.
Yeah.
Okay, alright. Is it because there's only one upper bound, so it has to be least?
No, no, I mean, this is an axiom.
Okay.
Okay. So real numbers are some set, the two operations. You can do algebra, it's linearly ordered and complete.
Okay,
That's what you mean by real numbers.
okay.
I mean, as for warm-up exercise, least upper bounds are unique.
You want him to write that down?
Yeah, exercise. So if I give you a set, there is only one least upper bound.
Yeah, there's only gonna be one. Don't ask me to prove it.
Assume there's two.
Yeah, proof by contradiction, yeah?
Yeah, so suppose L and L prime. Least upper bounds.
You should write your L's as capitals probably, that way they don't look like ones.
Yeah, that works. Release upper bounds of a set.
Yeah.
Yeah.
That's to name the set?
Bounds of a set B.
But you gonna say that like L is greater than L prime or less than?
Greater than equal to?
And let's say without loss of generality.
Oh my.
L is less than L prime.
Just because it's the least upper
Yep.
bound, right? Okay.
No, strictly.
Strictly.
Yeah.
Okay, alright.
Because you have two upper bounds, they're not the same.
They're dis-
Right, okay.
Yeah.
And here's the.
So one must be less than the other.
Okay.
Because if it's linearly ordered, any two elements are comparable, right?
Yep.
So one will be less than the other.
Sure.
So, and that's a contradiction because now the other one is
L
that
prime
least.
is not the least upper bound, right?
L prime.
Then L prime is not the least upper bound. Okay, so the uniqueness follows pretty much from the wording of the problem. Now, what we would like to understand is
Sorry.
there is only one real numbers. There's only one model. The real numbers are uniquely determined by these properties.
Determined by these properties.
I was thinking about that noise. When I came here and there were so many workers out there, I was already suspicious.
They don't understand, we got the Doberman in here. Great words of wisdom he's pouring into our ears.
You're delaying.
Okay,
the
so
focus of science.
the real numbers are uniquely determined by these properties.
That's your claim?
That's why I was talking about the natural numbers. there are different models for the natural numbers.
Okay.
But with what we wrote down,
There's only
the
one.
real numbers are uniquely determined.
So what you're saying though earlier about the natural numbers is you can make a different set of axioms that will hold under.
Same set of axioms.
Okay, same set of
Different model.
What the heck does that mean? I figured the model is the axioms,
No,
right?
the axioms only tell you how it looks like.
Okay.
Okay, if you say a car has 4 wheels and maybe you have to add a little bit, drives by itself as a motor or so. So you
Right.
write down a few things that characterize a car,
Okay.
but then you can have a
Plus.
Fiat Bambini or a Ferrari F350, right, also.
350. They had a 360 and a 355. I remember there being a 350.
So the axioms don't really determine what car you have.
Okay.
But the statement is, what we wrote down completely describes the real numbers.
You're only gonna get this one model. I guess I'd have to see you write those axioms down and then come up with different models for the natural numbers.
We did, right, I mean, the axioms are the real numbers.
Yeah, but for natural numbers, like to see the actual
Yeah, no,
different
no,
models. I know, it's beyond us, it's okay.
No, it's messed us almost over.
Oh, it's gonna take more.
There's enough time.
No, they might do this in 455 or so.
That's what you have to look forward to.
I think I'm taking it.
Ever. The above axioms describe real numbers completely. In other words, if R and R prime are two systems, two real number systems, then there exists a map E from R to R prime. So that phi is linear. Okay, so phi of alpha plus beta is phi of alpha
And parentheses, yeah.
plus phi of beta and phi of alpha beta is phi alpha phi beta. And all of the certain and budget. Okay, so you have a bijective map that preserves all of the structure that there is. And that means maybe you use different letters, but it's the same. Okay, so you're invited to construct phi.
It's an invitation I'd like to decline. What do you,
And the same thing.
No, I think this is nice because you have this incredibly powerful completeness statement. Completeness is overwhelmingly powerful. You can do lots of things with it. And to see how strong a statement can be, that's why I was doing this.
Identity function? Identity?
No, I mean, R and R prime by assumption are not the same. There is no identity.
Could you just take some generic function? I don't know.
What is a generic function?
I was gonna say like x squared, square the number or something like that. I don't know. You know we're not gonna crack this.
Well, you can do some. I mean, certainly R and R prime have to contain the, I mean, they have to have a 1, right?
They have to have a what?
A 1.
A one?
Yeah.
A one?
A one,
A one.
a wand. He is a wizard, but you know, we're not there yet. The math magician.
Yeah.
In Doberman's world, 11 is not prime. You remember that from the other lecture?
Because one of our axioms was that you have a multiplicative neutral element. Okay.
Okay. Multiply by 1, you get back what you started with.
Right.
Yeah.
So you have a 1.
Okay.
You have a zero also.
Oh, okay.
Add 0, you still have what you had.
But this one, n. Okay, because if you add 1 n times to each itself, you get n. N means 1 plus 1 plus 1 plus 1 n times.
Okay.
So, plus minus, because you have negative inverses. So, this set contains the integers, right?
Yeah, what you just showed. The stacking.
And because you have multiplicative inverses.
Rational numbers.
So here we have R. In here we have Q. Here we have R prime. We have Q. And our map better be the identity if it's supposed to have this property, right? Automatically, the map must be the identity on the rationals. Because if one map to anything but 1, then when you multiply with it, the value changes.
Okay.
So, if I give you any element in here now,
What do you mean?
We have to map it someplace over there, right?
Okay.
Map its cube?
No, R prime is a
Oh.
number of R. Yeah, I don't understand.
So, let's say, MR is the set of Q. So the Q is smaller or equal to R. So look at all rational numbers that are less than R.
Okay.
Then you have P of MR. Okay, so you can look at the images of all the rational numbers, right? This is
What was the images of the
a
rational?
subset of R prime, right?
Image of the rational.
Oh, what's the image of the rational numbers? I don't understand that statement.
We said here we look at the rational numbers that are less than R.
Yeah, okay. What's the image of that? Is that what you're asking?
We looked at images of sets, right?
Yeah.
So just take the image of that set.
Okay.
It's bounded, right?
The phi is bounded or R prime is bounded?
This set is bounded.
Yeah, there's, I mean, you set a stipulation with the R, that's why, right?
So there is a rational number that's bigger here. So there is a rational number
Bigger there.
bigger than here. So this is a bounded set.
Okay.
So let's take the least upper bound of this set.
Is that R?
No, because that's
And
the
say
image,
this
right?
one is
So it's phi of R.
Okay.
R is
Yeah,
the
yeah,
upper
yeah.
bound there, but in this
Yeah.
phi world, it's going to be phi of R, whatever. Invite us to prove this. You knew we could never do this, this guy.
no, but the point is, this is your map. You have to prove that this map is one-to-one, onto, and linear, order preserving.
Wait, one to one.
We said it
Onto.
should be linear, order preserving, and projective. Right?
So you got to prove all those pieces. You were invited to do so, Mark.
Let's see if I can even do injectivity.
Okay, let's do injective.
Okay.
Yes, guide me.
Balls.
Let's see, where should I write it over here?
The top should be good enough. 4 lines should be good enough.
Yeah, remove your claim stuff, dude. All of that.
Claim fee is 1-to-1. Okay, you want to show, take, start, say, suppose, R1,
Lowercase
R
r.
sub 1, lowercase r1, yeah. Less than R2, less, strictly less than R2. And
Mem-
little R.
Yeah.
So there exists.
An R prime? R1 prime or something?
First of all, there exists a cube. There exists a cube. little q. And q is bigger than R1 and less than R2. There is a rational number between R1 and R2.
So Q is between R1 and R2 is what he's saying. So write that out, R1 less than Q less than R2.
Such that Q's larger than R1.
Yep,
Okay.
Q is between R1 and R2, put it that way. Das ist gut.
Okay. And probably you have to prove that first, right?
Yeah, there's something lies in between, right?
Lemma.
Let's believe that for the moment. Okay? Then Q belongs to an element of M R prime.
Prime.
Fine.
Yep.
Okay.
Not important. The R.
Oh, I see.
Oh,
Capital R.
So
No, no.
R, no, no, R.
lowercase r, but there's a prime on that R.
R2.
Oh,
R2.
R2.
Okay.
And Q does not belong. Q, not element of MR1.
Yes.
Because we went with those rational numbers up to a point.
Because it's definition of error.
Yeah, Q is gonna be stuck with R2, right? Yeah.
So the least upper bound just by review, element UV, least upper bound.
So.
Of
MR2. No. Of 5.
Oh, let's do one other thing first. Let's say that phi
Suppose.
of, no, n
And
also,
also.
phi of q,
Little q or
phi of q. Phi is a map applied to q. No, phi open parentheses.
Like a
Oh, I
function.
see,
Yeah.
Q belongs to phi of MR2. Little r. And phi of Q does not belong phi of MR1.
Phi, bro. Yeah. Yup.
So the least upper bound of
Of
phi MR1 is smaller or equal. No, well, smaller. Straight, no, yeah, smaller or
no, it's just strictly smaller, right?
strictly smaller.
It cannot be equal
Yeah.
to
to
Q.
the phi of MR2.
Of phi of Q
There you go.
Okay, I see.
less than least upper bound.
MR2.
Right. And least upper bound. The left-hand side is phi over R1, the right-hand side is phi over R2. Right, by our definition.
Okay, yeah.
And we have strict inequality.
The definition of the least upper bound is that line right there, Mark. Phi MR2 equals phi of R. So you can rewrite that
Okay,
line.
alright, so just rewrite it basically.
Phi of R1 is less than.
Yeah, so equals, no, just by equal. Phi of R2. And the expression to the very left, your first expression was phi of R1. And you can put a strict inequality sign there. So phi of R1 is less than phi of R2. So they are not the same. R1 was not equal to R2, and we concluded that phi of R1 is not phi of R2.
And phi is the image, right? So they map to two different images is what you're saying.
So
Unique.
it's injected.
Yeah. Oh.
I'll subscribe.
Haha.
I'll subscribe.
That's right.
Yeah.
So it's not horrible.
I didn't prove it myself.
So how do you get onto subjective?
What is surjective again? It's the opposite, right? Each B only has one A.
Yeah,
Get
all the
subjective.
images, all the images.
Start out with anything here.
Oh.
Look at all the rational numbers elements. So this element is the least upper bound for this set of rational numbers.
Yep.
Go back. That's identity.
Okay.
Take the least upper bound for this set. It will map to this least upper bound here.
Okay.
So the map will be on. I mean, technically, it's probably more complicated to prove something like this one. But it's not horrible.
You're just adding the images, huh?
Right, but you have to first take those numbers, they are least upper bounds for a certain set of rational numbers, and you have to see what happens if you add those rational numbers.
Is this gonna be homework or what?
No,
Thank God.
Spend all weekend.
I don't enjoy
no,
you.
what I wanted to say is sometimes you make one elegant definition, and there's an incredible amount of power in it.
You mean of
This.
completeness, or you mean of?
Completeness.
Okay.
Oh, so when you say that there's an incredible power to this completeness, we're using this idea of completeness, this boundings on the sets to prove all of that
And
junk
you prove everything thereafter just with a few words.
because we have this bounding quality. Okay. You know, this
And
would be on-
sometimes things
this would
are
be on the
unique.
web.
Most of
It's
the
not a
time
test,
things
though.
aren't really unique. It's
That's your
difficult to
nothing.
describe that. But here you get something that's unique. Okay, enough for today. Oh, I could go on 5 more minutes.
Go, we're right ahead.
No, no.
I still got the camera going.
It's fine.